Welcome back to Inorganic Chemistry. In this second lecture on Chapter 8, we'll talk about the chemistry of the alkali metals. Before we saw our guiding framework for understanding the main group chemistry or descriptive chemistry of the elements, and we looked specifically at hydrogen, which doesn't fit very well on the periodic table. Now we'll start with the group 1A, the alkali metals. Alkali is Arabic from the ashes of the plant, and this is where these elements were first discovered and isolated. Alkali also means basic in terms of acid-base properties, like alkaline batteries have a basic compound in them as opposed to standard batteries. So this also comes from that name, alkali, because the ashes of the plant have a bitter taste, and you could heat the ashes, and the compound that melts and forms a liquid would be the alkali metals, which you can isolate the element from this molten salt electrochemically. We'll talk more about the chlorine part later when we look at the halogens. Now, as we said, the alkali metals, from the name, we expect it to be basic, and sure enough, the oxides are basic. So here we have potassium superoxide. When it reacts with water, forms potassium hydroxide. Another benefit, though, of the potassium superoxide reaction is that it forms dioxygen, or molecular oxygen, and indeed this solid here is used by NASA to produce oxygen and also to scrub out carbon dioxide on space missions. So all of the alkali oxides are basic. Let's look at some other properties of the alkali metals. So as we go down the group, the ionization energy decreases, just as we'd expect from the periodic law. Lowest member of this group, francium, is radioactive, and so its properties are not as well known. Reduction potential, which measures how easy it is to reduce, so you'd expect that as you go up, since it gets harder to ionize, so this should be the smallest negative number because it should be the easiest to reduce, but it is actually the largest negative number, and this shows a difference in our periodic trends for reduction potentials. While the metals are good reducing agents and bad oxidizers, they do vary somewhat in the first row, and this is an example of the uniqueness principle. So in the uniqueness principle, the first row in the groups has properties different from the rest of the elements in the group. And this is true as we go across the periodic table. Now, why is that? Because it's very small. We know from the periodic trend as we go up the group, the radius decreases, and there's a big jump here which causes bond lengths to be different, for example. It also is going to change the solvation enthalpy. So ionization energy is measured for the gaseous atoms. Center reduction potential is measured in aqueous solutions. So the solution or solvent is going to have an effect, and indeed the very small lithium ion that's formed, lithium plus ion, has a large solvation enthalpy. It gains a lot of energy by being surrounded by water molecules, and so that's why there's this change in the trend as we go up the periodic table for the first row. So that's an example of uniqueness of that lithium ion because it's so small. Also, we see lithium oxide is the favored oxide as opposed to sodium peroxide, and then potassium, rubidium, cesium superoxide, because this superoxide is big and this large cation can stabilize it. Lithium is very small, so it can only react or stabilize with the smaller oxide. Another unique chemistry of the lithium is its reaction with nitrogen. The other alkali metals do not react with nitrogen, and so if you are working with lithium, say doing lithium battery research, you need to work with an inert gas such as argon rather than using nitrogen as your inert gas. Another couple examples of lithium's unique properties. So lithium chloride, if we look at this computer model of the electron density around lithium chloride versus sodium chloride, we see, it's kind of subtle, but you can see that this sphere around the chloride is actually not as spherical as it is in the sodium chloride case. There's some distortion there, and that's because this lithium ion is so small that its charge density is so large it polarizes the chloride electron cloud, and that polarization leads to a more covalent type bond. Is this true? This is a computer model. Is this true? Well, lithium chloride is more soluble in polar solvents than sodium chloride. Again, this is a unique property because of the very small size of the ion. Let's look at a couple other chemical examples of the alkali metal reactivity. Metals can react with liquid ammonia to produce what are called solvated electrons. So in this unbalanced equation, if you have solid sodium metal, of course if we react with water, we know that's very exothermic. If we react with ammonia, we are able to somewhat isolate the electron from the sodium atom because it is solvated by the ammonia molecules. And this gives the solution a blue tint. And this is a very good reducing agent. So you can do reactions. For example, you could reduce the phosphorus carbon bond in triphenylphosphine if you react it with sodium metal in liquid ammonia to produce, actually, let's balance this, produce sodium phenyl and sodium diphenylphosphine. So this is an important reaction in making ligands, like we'll talk about in a couple weeks when we look at coordination compounds. Bis diphenylphosphine this sodium phosphide is very reactive and can displace the chlorides, say dichloroethane. Well, we got to do that twice, but anyway, get the idea. Some very reducing chemistry, strong reducing agents as we've seen. Another interesting chemical properties, chemical reactivities of the alkali metals is their reaction with crown ethers and cryptans. And this discovery resulted in the Nobel Prize in 1987 for Cram, Peterson, and Len. So the alkali metals, the ions, are very similar. So how can you separate them? Well, these ligands can be designed to be specific. So this is called 18 crown 6. If you look at the, not the flat picture, but the three-dimensional model of the molecule, it looks like a crown, and you can see there are 18 members of the ring if we count around here, and there are 6 oxygens in the ring, so hence the name 18 crown 6. This is selective for the potassium ion. This ligand here is called a cryptand, and its code name is 221, because you see on the bridging arms here for these triamine there are 2 oxygens on this link, 2 oxygens on this arm, and then only 1 oxygen on this arm. So 2, 2, 1. And this is selective for the sodium ion. So we could separate sodium ions, potassium ions with these different organic ligands.